Now that first table was all associated with polynomials in one variable. There are, in fact, though, polynomials in more than one variable. So on the handout, I've given you a statement about polynomials in two variables. So as you look at that polynomial in two variables, once again we have this idea that the number out in front, the coefficient a, has to be a real number, and then each of the exponents, n and m, have to be whole numbers. Now, I've given you things in terms of x and y, but we can write down polynomials in any two variables that you want. So an example of a polynomial in two variables would be negative 12 p to the fourth q to the seventh. Now, as you look at this once again, you can double check. Negative 12 is a real number, and 4 and 7 are both whole numbers, so this is definitely an example of a polynomial in two variables. Now, a lot of the definitions we were looking at a moment ago still apply. So this particular piece, if you look at all those different chunks, negative 12, p to the fourth, and q to the seventh, they're all connected by multiplication. So that means that this is in fact a polynomial of only one term. And because it's a polynomial of one term, that means that this is a monomial in this world of polynomials in two variables. So now that I know it's a monomial and the idea of monomial, binomial, and trinomial still apply, there are, however, definitions that do change. So in this world where we're looking at polynomials in two variables, the degree of a term definition changes. And I've given you the statement that the degree of a term in this world of polynomials in two variables changes, and the degree is going to be then the sum of the exponents. So when we look at the exponents on the variables, we have p to the fourth, that's the first exponent, and then we have q to the seventh, that's our second exponent. So if we add those two together, we're going to get 11. So the degree of this term is 11. Now you want to be careful on this one not to try to use these ideas for polynomials in one variable, because this idea of adding the degrees, adding the exponents doesn't really apply in the previous problems. So this adding only works if you're looking at a polynomial in two or more variables. So now that we have that, then you could then continue and talk about the degree of the polynomial. The degree of the polynomial then in this case would be also 11, because the highest degree in this particular problem is 11. So now that we have that idea, the last idea that we're going to be talking about today from section 5.4 is the idea of adding polynomials. So in example 1, I've given you two polynomials, x squared plus 2x plus 5 and 3x plus 7. If you take a moment and double check all of the definitions, you're going to see that everything is fine in terms of polynomials. All of these exponents are whole numbers, and yes, these are both polynomials. So how do we add these two polynomials? Well, the answer is we actually have two different techniques. One is a technique that we talked about earlier in the semester back in chapter 2. We can actually come in and combine like terms. So in order to combine like terms, the first comment is that these parentheses really aren't doing much for us. So because those parentheses aren't doing much for us, we can drop the parentheses. And once we've dropped the parentheses, in this world of combining like terms, we can reorder our terms, because remember, addition is commutative. And because addition is commutative, I can put terms that look like each other next door to each other. Now, we talked about this early in the semester. If it's a step that you need to write down, write it down. If it's a step that you can skip, feel free to do so. So I'll write it just in case you want to see it. So x squared, he doesn't have any friends, so I'm going to move on. And then we have a plus 2x. Well, another term that looks like him is 3x. So I'm just going to reorder and put that plus 3x next door to that. And then we have the addition of a 5 and the addition of a 7. X squared, once again, doesn't have a friend. He's just going to come down. And then 2x and 3x come together as 5 of those x's. If I have 2 of these x guys plus 3 more of those x guys, in total I have 5 of those x guys. And then finally, 5 plus 12 is going to be 5 plus 7 is going to be 12. So there is our answer for this particular addition problem, x squared plus 5x plus 12. But later on we're going to be talking about some of the other things we can do with polynomials. And it's nice to be able to see that we can take this same problem that we've talked about before and just write the process in a different way. So you'll notice over on the right-hand column, I've given you a statement that says we can also do this same problem using option 2, which is using columns. So let's go ahead and talk about how to add something like this with columns so we're ready to use those ideas later on with some other kinds of problems. So the first thing you do when you write down this kind of addition problem in columns is to just write down your first polynomial. So we have x squared plus 2x plus 5. And then I'm going to write down a plus sign. And then I'm going to write down my second polynomial. But I'm not going to write down my second polynomial just any old way. I want to make sure that I'm lining things up so that every term that has the same exponent on the x is lined up in the same column. So my first term in the second polynomial is 3x. Because that has a power of 1, I don't want to write it underneath the x squared, because that has a power of 2. So once again, the whole idea here of adding these in columns is to make sure that everything in terms of the same power is lined up. So x squared, well, I don't have an x squared in this one, so I'm just going to move on. So my next column here has a 2x in it. That's an x to the first power. I have an x to the first here, so I'm going to write down my 3x directly below the 2x. And now those two pieces that have x to the first are lined up in the same column. And then similarly, I'm going to put the plus 7 so that the constants are lined up here as well. So now that I have this, then I can go ahead and add my polynomials. Now, one of the things to note about addition, when you did this with just numbers, you always had to start at the right because there was the possibility you might have to do some pieces of carrying from one column to the next. Well, in this world of polynomials, you don't ever have to worry about that. So in fact, you can start at the left if you want to, or you can start at the right if you want to. It really doesn't matter. I'm going to choose to start at the left just to say that I can. So we have x squared here, and no friend down here. X squared is just going to come down there as x squared then. And then in my x to the first column, I have 2x and 3x. Those are going to add together as a positive 5x. And then finally in my constant column, I have a 5 and a 7. Those are going to add together as a 12. Now, as you look at the left-hand column and the right-hand column, you're going to see that I got the same answer either way, by thinking about this in terms of combining like terms, or by thinking about this in terms of adding by columns. But you want to make sure that you're comfortable with both techniques, because again, this idea of adding in columns is going to come up later in other sections. At this point, we're done with this particular handout, so you're ready to go ahead and check out worksheet 30, and then you're also ready to do homeworks 30. Have fun.